Welcome, colleagues. A real pleasure to have you all here today again for our penultimate, our final, our final Innovators in Analytical Chemistry symposium. So we're finishing with a bang, with an excellent speaker. So I want to introduce Professor Patricia Forbes from the Department of Chemistry at the University of Pretoria in South Africa. I had a pleasure working with Patricia on a nice article that we wrote exploring the comparisons between different analytical curricula around the world, which was a great experience in writing that article. And it's a real pleasure to have Patricia talk to us today as part of our webinar series that we've been hosting. So with that, I just want to introduce Patricia's presentation, which is Opening the Box, a self-ensemble spectrophotometer for active learning. And over to you, Patricia.
Thank you very much for the kind introduction and also for the invitation to present here today. I'm interested to share the story with you. I must say, when I prepared the presentation, I got quite nostalgic because it's a process that has happened over quite some years, as you've seen here. So yes, you've heard I'm based at the University of Pretoria, and like anywhere else in the world, our motivation in training analytical chemists is so that they think in terms of what is actually inside the box of the instruments that they use, and their practicals, and that train them on. And we know, I think all of us on the call as analytical chemistry educators, that often students see instruments that we utilize as some magical black boxes where we put a sample in and by magic you get some number out. And that number, of course, must be correct, and you don't think anything further about it. And so the idea was that we really wanted to explore what was inside the box of our commercial instruments, which are built as such to be rugged and give us precise and accurate results. But in terms of analytical chemistry education, they are rather confined in what students can actually explore, especially when it comes to something like a UV spectrometer. The students would typically open the lid, put a cuvette inside, close the lid, and press a button and get an answer. And so we also have constraints. Being in a developing country, cost considerations are important when looking at what instruments we can provide in our undergraduate classrooms. And also we were having high student numbers. This has since curtailed. After COVID, the numbers came down and haven't really recovered since. But at that time, which was now 12 years ago or so, we were seeing very high student numbers, particularly in our third year BSc chemistry curriculum. And we needed to make sure that these students got access to equipment, hands-on access, so that they could really learn these techniques and better understand them. So the idea was that I wanted to develop a kit that's the third year analytical chemistry students could actually build their own spectrophotometer using the components that we provide in this kit. And we then wanted to be sure, though, that aside from just building it, that it could actually generate useful results. So not just some general concepts in terms of spectra or something like that, but actually results that made analytical chemistry sense. And so we wanted to have this kit that we could then run some practicals in parallel to the theory that we were giving in the lectures, so that the students could really learn about the components of the instruments and their relative properties. So when we started with the project, we thought, now what are the possible components of a do-it-yourself spectrophotometer? What are the options that are out there that we could potentially use? And of course, if you look and you Google, you'll find things like this. So these kind of cutouts that you can print out onto card. Often they use old CDs, for example, to provide spectrum, but these are too simple for third year analytical chemistry. They don't have all the components that we wanted to teach our students about. And also they find to general understanding of spectra, but are not providing the analytical chemistry worthy type of results. So another option are off-the-shelf educational spectrometers, such as this one that you can buy from Thor Labs, and indeed is pretty impressive in terms of the components. And maybe in some countries, the cost would be seen to be feasible, but in Africa, this would still be rather tailed. Maybe you could get one for a laboratory, but then all the students wouldn't access to it. We didn't get that hands-on experience that we wanted. So we then looked at alternatives, and I came across a publication by Jane Thomas Oates, the University of York, and they had a publication, Education Chemistry, where they had a do-it-yourself spectrophotometer that consisted of the components that are shown here. So they had a general white light source with the lens and grating. And so by having the light-dependent resistor, measure the resistance, and by calculation then work out the transmittance and absorbance. In this case, you can move the slit as it's positioned currently. Green light would pass through to the sample, and then by changing the position of the slit, you could then have blue light passing through, for example. So this is one option. You can also replace, you could also move the grating instead of moving the slit as it's shown here, or you could even use colored filters. The problem with the colored filters is that you then get very limited data points, now depending on which filters you have, and also the intensity of light that you get through to your sample is very low, so your sensitivity is impacted. So looking at the electrical system that is Thomas Oates' device employs, and how the cuvette is positioned on the circuit board, that was rather a concern for us, because in terms of using this instrument repeatedly with students, the potential that they would pour their samples into the cuvette while it was on the circuit board is very high, bright, and we wanted to make sure that it was more rugged than that. So we used this as a base for our design, but we looked at having something slightly different. So we had to decide what would work for us, primarily focusing on analytical chemistry students as our target audience, but bearing in mind that there are many other disciplines that also use spectrophotometry. Food science is shown there on the list, and I'm going to mention them again later on in this presentation. But it could be, for example, in electrical engineering or computer science, you might want to target students in those fields, and then you might use quite complex electronics, such as this example here, another homemade spectrophotometer. But in our case, we didn't want to go that route. It made the machining rather complex and therefore costly. So we rather relied on a more simple design based on that of Thomas Oates' paper. But you can see in the top, you can see over here now we've removed the cuvette from the circuit board and rather made it more rugged and also simple as a result. You can see here that we power the circuit board just with 2 9 batteries. So we started with various prototypes, and at this stage, a third-year student, Tuva Nothling, who was doing chemistry and physics as his majors, joined me to complete a little project on this. And you can see in these pictures that we had very basic designs to start with, just using cardboard, little rollers on rods to get an idea of the type of distances we needed, the type of size the instrument could potentially take, and what components we needed and what type of configurations. You can see here we use an old cooler box, a polystyrene container that we coated with some black paper on the inside to house our device initially as well. So we didn't have any stray lights. Maybe before I move on, I can just say that Turvin subsequently completed his PhD in fluorescence spectroscopy. So I like to think that this was just the start of great that then came following that. So the final design we called the SpecUP, the spectrophotometer of the University of Pretoria. So University of Pretoria is abbreviated to P. And you can see in this photo here that we have this cover over the device, which Turvin's mother kindly made for us at that time. You can see that it had a little window over here that you could look into to see what was going on inside. The question is, okay, well, so what was inside our box? What did we use in our final design? And the important thing that we did that has made a big difference, I believe, in the novelty of this particular spectrophotometer rather, and also the learning opportunities that it presents, is that we assembled the different components onto these movable drawer draw hinges. So they are movable. So the idea is that the students have to really look at optimizing the positioning of the light source, which is an LED, to that of the lens and potentially a grating if we use one, if we're not using a colored LED, to the sample, then with the light-dependent resistor behind that. So it has many movable parts, and there's a lot of optimization that needs to be done. And that is really the interesting part when it comes to using this device for student teaching, because it's something the students don't always think of when they use a UV vis because of the lack of interaction they have with the instrument. They don't think about these various optimizations that need to be done to get the best results you can. So initially, we used machined parts made out of metal, as you can see here. So it was just an old piece of wood. You can see the draw hinge over here. So everything is movable relative to each other. So we can optimize it. Here we see the white LED. This is a diffraction grating. It's a cheap one that you bought that you can use when you use the white LED. And here you can see a sample with the light-dependent resistor behind. And here you can actually see, if you look carefully, that with using this diffraction grating, we can see the colors that we can now access in terms of interacting with the sample. So I just have a beautiful video. So this is one of the early prototypes. You can see here that the LDR and then later also the LED are connected to the circuit board, which is being powered by batteries. And you can see here how the light comes on. And as you can see, the person was doing that, there was also quite a bit of movement in the positioning. And here he's also optimizing that, looking at the size of the dot and the intensity to optimize. So there are two modes of operation overall. The one is to use colored LEDs, and in this case, then you don't need the diffraction grating, but then you are limited to the number of LEDs you can access, but there are more and more of these available, of course. And if you look at the particular solution color you want to analyze, you need to then choose the complementary color of the LED, which in itself is an interesting exercise for students to think about. Alternatively, you can use a white LED, diffraction grating, and then manually adjust either the height of slit or sample, or changing the positioning of the grating. And then you can use color tables such as this one to get the average wavelength for a particular color of LED. Of course, we know that the LEDs are not perfect in terms of the spectra that they present, and that also is an interesting exercise for students to conduct. Alternatively, you can use a color chart like this to check which color you see, and the person's not colorblind, and then check what the average wavelength could be. So how much did it cost? Well, we're looking at, okay, we're talking rads, but I've put in here in euros for general audience. So for about 25 euros, you can build one of our SpecUps. And as you saw for the Thor Labs example, the cheapest you can get commercially is around 1,500 euros. So a big difference in terms of the number of these you can then have and allow the students to have hands-on experience. The main cost components at that stage was the aluminium plate that we were using for different parts to machine them, the batteries, and of course this is a recurring cost. Batteries do need to be replaced. Probably we replace them every 1 to 2 years. The multimeters that we use, it's a minor cost in comparison. Printing the circuit board, and then at this stage we were using that leatherette material to make the tent for covering the instruments, that we don't have the interference from background light. But later we actually started using blackout curtain material. So we just have a rectangle of that we use as a tent instead, and that reduced the cost. So there are a number of different applications. This is an example where we have used potassium permanganate, actually developed a calibration curve for the absorbance. And after doing that, you can then, of course, use this calibration to determine the concentration of unknown samples. In each case, we determine the V dark, so that's the voltage when the instrument does not have the LED connected and is covered time, and you should get a 0 measurement unless there's some interference in the circuit, and then of the solvent and the sample to be able to calculate the transmittance and then the absorbance. This is an example of analyzing green food coloring. See that there's a range of different concentrations that have appeared. And here's another little video just showing that. So in this case, we're doing green food coloring. So we're using red LED. First of all, disconnecting it so that there is no light. And this is actually interesting because when working with the students, often they think that even though the LED is connected, if they cover it, they're getting a V dark measurement. And that is also something that is interesting to teach them in terms of what a V dark actually means. So there you can see the 0 voltage on the voltmeter. That's reconnected. So you might see in some of these videos that things are moving. So this was a problem that we had. We had later improvements. I'll show you some of those. But what we did is we actually put the holders in place to make sure that once you've optimized the setup, that you can keep it in that position without having any further movement. Now it's covered again. You can see there was a bit of movement there, which is not ideal. That's why we had to correct that later. Now the new voltage measurement is taken. So even by doing very simple measurements, because of course, in some laboratories in less developed countries, having access to volumetric glassware is also sometimes a challenge. So you can even do it in a very basic way in terms of the number of drops of food colorant that you use with the syringe into a certain volume. You can use that and get a decent calibration curve, which is very useful. Also, interestingly, to show that if you were to increase the concentration too much, that you would lose the linearity, so learning there as well. And then with the red food colorant as an example as well, here you can see the non-linearity more. And interestingly, of course, you can also compare the two different calibration curves in terms of sensitivity that's achieved with the two different colored LEDs in terms of the slope of this. You can also use it to construct spectra. So again, this is potassium permanganate. This is the graph that was shown in the Thomas Oates publication. So comparing the commercial spectrophotometer, which is a solid line, to the points that can be obtained with their do-it-yourself spectrophotometer. So we tried something similar. And here you can see using the white LED and the diffraction grating. From the other view there, you can now see the spectrum. And what we then would do is with this particular model, this prototype that we're using here, we would actually move the sample stage down to allow the different wavelengths of light to pass through the slit and then interact with our sample. So in that way, with the white LED, you can actually get all the colors and wavelengths, and then this is the result that we got, this blue line there. So of course, you don't get the resolution that you do with a commercial instrument. We wouldn't expect to, but it is useful results, and it allows the students also to think about, why you see a difference in transmittance at different wavelengths based on what you see also with the commercial instrument. There are many other applications you can use. We did, for example, some kinetics with the iodine clock reaction that we could do. It's possible to do many different experiments when there's a color change indicated, such as the bleaching of crystal violet. With metal ion concentrations, we can interact them with various ligands and form colored complexes that we can then determine using different wavelength LEDs, such as shown in this example here in the publication. Even one, looking at the oxidation of alcohol dichromate. And interestingly here, there can be additional studies looking at how to remove pigments from red wine that could otherwise interfere with the results. So things like using activated charcoal paste to do so. So basically, any titrations, like in the second year syllabus in analytical chemistry here, we have a lot of emphasis on titrations. And so instead of using our eyes to determine the endpoint, we could also potentially use our SpecUP to determine that. But in all the experiments that we do, we make sure that we include the different analytical figures of merit to make sure that the students get hands-on experience in understanding what these terms actually mean and how they impact on the results that they achieve. So things like resolution, the sensitivity and selectivity, accuracy, and here we normally compare to results of the commercial instruments, precision and repeatability, limitations and sources of error, thinking of ways on how you could improve the measurements going forward. This is an example of a repeatability experiment using the SpecUP that Turbin did. So he did 3 repetitions, and you can see for such a simple instrument, the certain that. So in terms of educational outcomes, we wanted to make sure that the students got hands-on experience in terms of working the instrument and its components. Initially, we thought that the students could actually build the SpecUPs from scratch themselves from the different components, but this does take quite a bit of time. And usually we don't have enough time in the practical sessions for them to do that. So we typically have it already built for them, but then they work with it further. They can use it to calibrate the instrument, as you've seen with the food colorant examples, and that they get a better understanding of the relationship between absorption, light, and concentration, understanding of the analytical concepts I just said, and then for each particular experiment, there are normally specific outcomes that we have as well. But in the end, it's all about inquiry-based learning and really hands-on presence learning as well. So now I want to give you a bit of background in terms of where we were and where we are. SpecUP and the journey of SpecUP, or the evolution, as I've said here. So it started way back in 2012. You might have seen on some of those photos the timestamps. So that was when I first started the project, Turbin, and we were fortunate to get some funding from the Photonics Initiative of South Africa, PISA, which is really here to try and promote photonics training and research in South Africa. So that was in 2012. And then following from the successful design of the instrument, there was an international chemistry conference in Africa here at my university where I presented on the instrument. And then also I was invited to present on it at the International Conference on Education and Training in Optics and Photonics, which was in Portugal in 2013. And Turbin also presented at a Young Spectroscopist Symposium here in Pretoria. So this got the word out a bit about the SpecUP. And I applied for funding from the African Laser Center, so that's called the ALC, which is to promote laser research in Africa as well. And they provided training funding in 2013. I also wanted to better evaluate the impact of using the SpecUP, so I applied for ethical clearance from the university so that I could have some surveys to give people so that I could get a bit of feedback in terms of their experience of using it. And then we published a paper on the SpecUP in the South African Journal of Science in 2014. But going back then to the training, so I decided that based on inquiries that I then had after the initial presentation at the conference in Pretoria, there was a lot of interest that other universities wanted to also use it. And so the African Laser Center funding enabled me to host some SpecUP workshops. So the selection of participants was quite careful because the funding was used to pay for them to come to the workshop. And so there was a limited number of people that we could host, also because I had to then build the kits for each of them. So I used various criteria to select who should come, but basically it was for academics at different institutions that were involved with courses dealing with spectrophotometry, cracks or theory in matter, and that they then had the potential to actually use the SpecUP when they went home. This idea is that they actually were given these instruments that they took back to the institutions with them, and that they showed that they were keen to improve their students' understanding of spectroscopy, because they were required to write just a short motivation as to why they wanted to attend. So at these workshops, they were given a guide to, first of all, assembling the SpecUP, and also the different components that were needed in the kit, so that when they were back home, if they wanted to assemble more, that they could do so. And the first thing that we did at the workshops is that they would actually start building their own instrument. So we then would give them information like this in terms of, okay, this is the entire setup, and then for each component, how you need to assemble it. So as you saw, they were given each individual component that they then had to put together. By the way, this black over here that we used to hold the lens was actually from the inner of a bicycle tire, and bicycle tire inner that just to hold that in position there. And then we'd move on to the different experiments. So this food coloring experiment that you've already seen. So they were given detail like this in terms of the background, but then also the individual steps, the procedure, so that they had something they could use as a basis for their student practicals when they then went back home. And examples of the operation curve you've already seen. And then also some questions, like which color analysis is most sensitive and why? How would you determine concentration? What parameters were affecting the accuracy and precision, and how could you improve on these? And then an experiment looking at the absorbance spectrum of potassium permanganate, first of all using the colored LEDs, and then using the white LED, showing you both of these already. You can see it was detailed exactly how to proceed. And then also some questions that they could pose, again linked to the accuracy and precision, how to improve results, but also comparing to the commercial instruments, comparing the white LED to the colored LEDs. And so they also were given additional information to take home with them. So, other options for cheaper materials if they had trouble obtaining what they needed to, and some tips so that they could look at improving and using the instrument further. So the first workshop was held here at the University of Pretoria in November of 2013. And we had delegates from South Africa, but also from Kenya, Botswana, Lesotho, Swaziland, and Namibia. And you can see some photos here in the lab where they had set up their device and then they were doing various experiments. Following from that, I was asked to present a workshop in Tunisia. We went from south of Africa right up to the north. And this was upon invitation of Prof. Murad Zagal. See a big group of students. It was a lot of postgraduate students and young academics that were particularly involved in this. You can see some of the photos of that doing the food coloring experiment. And you can see it's very basic. There's no volumetric glassware here, but they're using syringes to add the drops of food coloring, doing the dilutions from there in these disposable cups. And then we had the International Year of Light. So this was 2015, and that was great because it allowed access to more funding to host more workshops. So then I gave this one in Grahamstown, also here in South Africa in 2015. And here we had delegates from South Africa, Zimbabwe, Swaziland, Zambia. And this was funded from the South African Department of Science and Technology and also from the Society of Chemistry. And you can see some of the comments. People really did appreciate it. And we're glad that they had some new ideas now for their practice. So it was very positive. And then I also want to just highlight some of the side stories because I got quite nostalgic putting this together, in fact, because it really has been quite a journey. And I highlight a particular person here. So Kampamwe Kabwe was one of the delegates at this particular workshop. And probably about a year later, he emailed me requesting that I supervise his PhD. He's based at the Copperbelt University in Zambia. And he then joined me and completed a PhD on fluorescence spectroscopy, actually. And you can see him at his graduation. So that was a fantastic outcome that was unintended. Also in 2015, we had another workshop in Tunisia to celebrate the International Year of Light. This was called Lighting Up Africa with Lasers, Optics, and Fibers. So it was a workshop that included a number of different activities, including the SpecUP. You can see this person here is deeply involved in what's going on underneath the cloth and what is happening inside the instrument. And then I mentioned food science. So at the University of Stellenbosch here in South Africa, they asked me in November 2015 to give a workshop there. They were keen to use the SpecUP in their practicals, and particularly they're looking at different natural food colorants was of interest to them. And in 2016, we had the Teaching the Teachers workshop, which was held in South Africa. It was also an optics and photonics initiative, looking at a number of different techniques, including SpecUP. And yes, the impacts of these workshops drew very good responses from the different applicants. And it was clear that there was certainly a need for this teaching tool, and that it was very well received by the participants. You can see some of the comments that we had there. It had a big impact in Africa. Here we even see that the Deputy Vice Chancellor of the Masai Mara University even sent a letter thanking us for donating the SpecUP to the institution, which was really great to receive. And following from that, in this letter, he actually mentions Mr. Lois Solano. And some years later, and these are the photos from that workshop, which I've already shown you. That is Alois over there. And he still uses the SpecUP at Masai Mara University for his student practicals. You can see that he's now encased it with wood instead of having the material cover. He's added wood components that he's now using in his instrument. And interestingly, he also contacted me and we set up a collaboration, some years in fact, that was related to air quality monitoring in domestic environments in rural and urban Kenya. This is a voice. So as of September 2016 then, we had a SpecUP user network that had reached 27 different institutions in 20 countries in Africa. And that really was helpful also to the African Laser Center in doing this job, because they really are trying to build photonic skills in Africa. So we had a very good partnership with them in this undertaking. So what about back home? What is happening here at the University of Pretoria? Well, I implemented using the SpecUP in the Analytical Chemistry 3 course, which I lecture already in 2014. Typically, we have about 40 students that are on third year class, and they work typically in pairs at SpecUP, and they use in a practical session both a SpecUP and a commercial instrument and then compare them. And interestingly, over the years, we have identified various limitations. I mentioned, for example, movement of the bar and how we have adjusted to improve that. But there have been a number of iterations in improving the original SpecUP. I'll highlight a few of them shortly. But just to mention that, as I said, I got ethical clearance because I wanted to have some questionnaires to get more feedback as to what, and a better understanding of what the educational outcomes were of using the SpecUP. So there was a questionnaire for students that have not used the SpecUP, and then there was one that they would use afterwards. And there was various questions in terms of their level of study, if they've used a spectrophotometer before, they've been taught theory thereof, and then also in terms of various questions around spectrophotometers, whether they're easy to use, if using it has helped them to understand the theory, and even questions such as do they have moving parts, and whether they agreed with those or not. There are also some more theoretical questions testing understanding of things like what is an LED and how you could change the wavelength of light to get an idea of the theoretical background of participants as well. So just a subset. So this is just some initial results that we had. When we look at question 5, have you ever used a commercial spectrophotometer? Quite alarmingly, almost, a good third had not. Whereas if you look at question 7, have you taught the theoretical aspects? They basically all had. So this is really showing the need for such an instrument. Then here, before using the SpecUP, questions like spectrophotometers do not have moving parts. Question 3, you can see in terms of the answers that there was quite a broad distribution, so people weren't really sure. And that is largely due to the fact that with the commercial instruments, you don't see any public. And then question 5, the only thing that is needed to be done to obtain a result from a spectrophotometer is to place the sample pipette inside the instrument. And again, there we see quite a range of results, some people not being sure, some people agreeing, and so on. And then question 9, I would recommend that all chemistry students get hands-on experience, unanimously agreeing that is necessary. And then after using the SpecUP, question 2, SpecUP helped me to understand, very positive response. I enjoyed moving the components to see the effect it had on results, very positive. Question 5, the SpecUP made me think about how spectrophotometer works, also a very positive result. So this was very good feedback to get. And yeah, so it gave me motivation to proceed and to continue with the initiative. So I used these questionnaires for some years. At this stage, of course, it was all on paper, which was not very environmentally friendly and also was rather cumbersome in terms of processing the information afterwards. But I think it's something that nowadays you can do via a little app or something and then get more detailed and ongoing responses, which would be a good thing, something I can maybe put on my to-do list going forward. So with this initiative, we took commercial instruments that we normally would try and explain in a theoretical course by drawing a schematic diagram such as this, to actually open the box and show the students what the individual components are so that they can really have hands-on learning and a better understanding what it takes to actually get the results that the instrument gives them. There were some more recent developments, and you might be thinking already, gee, it's quite antiquated to machine those parts out of aluminium. Yes, nowadays we can 3D print them. So first of all, there was a postdoc from the University of Glasgow who helped with developing the code for the different parts and designing them. And you can see here, this is now the new version of the SpecUP. And these poles here, these are here to help us when we cover and make a little tent with material to cover the instrument. That's what these are for. And the students were very happy with the new version of the instrument. That was much easier to work with than the previous one in terms of the different component holders. But I always said to the students, when working with it, if you can see anything you would like to improve, come and chat to me, open to improving it further. And some years back now, Otto Venter is currently doing his PhD. So probably this was about 3 years ago. 4 years ago, he came to me and said, no, he thinks he's got ideas on how to print these better in a way that makes it easier to adjust and also to make them more secure in their positioning. And so he came up with new designs that we then printed and that we are now using currently. So these photos I actually took 2 weeks ago. We are still using our SpecUps. It's 12 years down the line and they're still going strong, which I think is quite impressive that something so simple has stood the test of time. I must say, though, that I'm sure that nowadays the LEDs and the LDRs that we could obtain will be much better than these of 12 years ago. So that's also something in putting this together that I've thought I need to actually action so that we can improve the instruments further. But in conclusion, it's not only in developing countries where there's a need for this. We've seen in 2017, for example, that in the US was this publication also looking at having a prototype that students could develop and use themselves and gain this hands-on learning. So the advantages of our SpecUP is certainly its low cost, which allows it to be used very widely, especially in developing countries, but not only. I also had somebody in Italy who asked for the details and she's using it there. It's simple to construct. It's an open design, important so that you can actually see what's inside. It has moving components so you can see what happens to your results when you make changes. But the results are good enough quality for analytical chemistry teaching. And we can always adapt and improve it. And it allows inquiry-based learning. So I would like to acknowledge many people, the various funders over the years, particularly those from the National Laser Centre South Africa and the African Laser Centre, who supported the work in many ways. both from support and financial support as well. Then Leon Engelbrecht, he's our machiner arts here at the university, who assisted with the electronic circuit boards, and actually also Nico van Buren, who assisted with that. And then there were a number of students over the years. So Tuava Nothing was the original person that you saw. And then Bakama Buerta worked a bit with him to optimize it further. Sifiso and Sabande assisted with the workshops. So one of my trainers, he was doing his MSc with me at that stage. He continued with his PhD in spectroscopy. He's now a faculty member here. Monet van der Linde is in this photo here. She helped with inputting all the data from the questionnaires as a project some years back. And Erms, who was the first person to develop 3D printing, and Otto Louis followed on. And then Professor Thomas Oates. So as I said, our initial, her publication was a fundamental component in developing what we have. And she was always very open to chatting about it and very enthusiastic about the SpecUP. And you can see the photo that I took here with her when she came to South Africa for a conference some years ago. So that was really wonderful to meet her. This is the paper. If you are interested to read further, you can see some information there. And then we were very fortunate in 2015, this project won the Reimagine Education Award in the US, President's Land. So with that, I'd like to thank you for your attention and also for the opportunity to present here today. And if you have any ideas on how to improve our SpecUP further, or interested in doing some outreach with me going forward, because I think it's something, as I said, I got quite nostalgic putting this together. And I think now that we have the 3D printed components, perhaps it's time for a phase 2 of some outreach activity. So thank you very much.
Thank you so much, Patricia. That was a really illuminating presentation of really opening an analytical instrument. I think the impact of not only making it accessible, but also opening it so that people can learn about the components of an instrument are really important, and things we forget now when the boxes are closed. But also really the impact that it's had across the region and wider is phenomenal. So, you know, that is an incredible achievement, I think, in that context. So I'll open the floor to questions. We've got one already from Dr. Ramprakash, if you like to ask a question. Okay. Don't know if anyone else. Yep. Joe, Kickle.
Thanks so much. That was great. I loved seeing how many workshops you had done and how this had spread across the entire continent. And I wondered if you could say a little bit about what you learned as you went through different iterations of those workshops, because I think doing faculty development, in some ways it's like teaching students, but in some ways it's quite different. And I can imagine that each one is bringing their own institutional context to the activities that you're doing in the workshops. And so I wonder if you could speak to that a little more.
So I didn't really tailor the workshops for specific regions or faculty. So it was basically the same thing each time, but it was interesting to observe how different people responded to it. Because, and it's the same even in the practicals, to be honest, because there are definitely some people that enjoy fiddling with things and get it right, and the others that just get frustrated, which is interesting, because there's not necessarily a direct correlation between, you know, marks and their level of interest in it. So I think for some people, they want to get a device that, you know, they can just use, and there are others who like to build something and make it their own. So that was an interesting thing to see. But I think for the most part, yeah, people generally seem to enjoy building the instrument and then seeing what it could do. There are cases where there are challenges because, for example, and I think that this is also leads to what I said about getting new LEDs and LDRs, because there are some little tweaks that you need to make, and sometimes you do get a lens that's a dud, because these are very cheap lenses that we buy. So maybe, you know, the light will go in a funny direction or something, and you need to make a plan. And even, what I've seen is sometimes with the circuit, we actually have it sitting on a piece of aluminium and there's press stick between the two. But if the students, push it too tight, then you start having shorting and then you get, so there's all these things that come up and learning opportunities along the way and problem solving that people need to develop. So yeah, some people are more keen on that than others.
Yeah, thank you.
Any other questions from the audience?
I'd like to ask if I can just also mention a little bit about our IUPAC project. Okay with you. Because I think that this forum brings together kindred spirits, and so it'd be good just to make people aware so that as the project moves forward, hopefully they can be part of that. So I think probably also in some of the previous presentations in the series, this project of IUPAC has come up, where we're looking at reviewing the current status of analytical chemistry education. And we had a project meeting during our recent IUPAC General Assembly and World Congress, which was held in Kuala Lumpur. And this project is based on the premise that there's a lot of anecdotal evidence that analytical chemistry as a discipline is being eroded. And a lot of what analytical chemists do is now being found more in the applied sciences, and the rigor that we like to train our students on is sometimes then lacking. So we wanted to look then at the curriculum in different parts of the world and also get a sense in terms of what is happening in terms of professorships in analytical chemistry and funding and the quality of analytical chemistry education. And the idea is that ultimately there would be some outcome in the form of a white paper or report or similar, which can be used then by different institutions going forward. So the project was started in January of 2020, and Zoltan Meister was the project leader. And the project is done in partnership with the Chemistry Education Division of IUPAC. So in 2020, we thought we were all systems go, and then COVID hit, and there was basically the project was on hold for some time. It was then only relaunched in 2023. At this time, the project team was sort of reassembled, and two subgroups, one on academic, focusing on academic stakeholders, and the other on industry stakeholders were formed. Mentioned in my introduction the journal publication that is really an output of the activities of this project. And both the academic and industry sections groups have developed questionnaires that we want to distribute. And this is really why I put this here, because I'd like to request that through this initiative that we can, hopefully once these questionnaires are finalized, that you can assist us in distributing them, so that we can get really holistic and good feedback that will make the results of the project new. So we'd really appreciate your participation, and I've put my email address here. I think if it's okay, through Marvik and Michelle, we can distribute the questionnaires going forward already. But please, if you can distribute them widely amongst your networks, previous students that are now in industry or in other academic institutions, it'll be great, because the more information we get, the better.
Sounds great.
Absolutely. Yeah, I think me and Michelle have both been part of the project, so I think we're very keen to support this distributed as wisely as possible to get as much insight into our global community of, as you say, shared kindred analytical chemists, I think, around the community. So yeah, absolutely would be delighted to do that. Is there any other final questions for Patricia? I know she's hanging in there at what's coming up to 6 o'clock, I think, South Africa time. So any other final questions, or we might disappear? Michelle, is there any roundup you want to give before?
I did just want to say, this is our, like you said at the beginning, last webinar for this year, but we're planning to take a short hiatus and resume in the spring. I'm going to put into the chat a link to the playlist of our past recorded webinars, and I'll also be posting the recording of this webinar. I'll send that out in an email, not just to the folks who are here, but also to the people who are on our subscriber list. And I think we'll also be sending around a poll to see if there might be a more optimal time for people to attend these live. But thanks to everybody for their participation, those of you who are here live right now and the people who watch these videos later. And thanks so much to Professor Forbes for speaking with us today about this really cool long-term project.
You're very welcome. Thank you.
Right.